Welcome back, everybody. So we're going to start up my favorite part of the of Unit 3. So we start talking about all the tests. We got four tests to do today, and then on Thursday we have three more tests to do for a total of 20 million, whatever it is at this point. And then on next Tuesday we'll have a day to practice just going through all the different tests and like when to use them, much like with integration techniques, right? There's some dead giveaways on things that kind of tell you which test to use. So we'll have a lot of practice that day. But until then, we've got to get through the tests. So this was a fun thing that got discovered after integration became a thing. So we haven't talked about it yet, or we haven't given it a name, but the sequence that is just adding up all the fractions, like all the fractions with an integer coefficient of 1 up top. So 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. One over the sum from n equals 1 to infinity of 1 over n. That is called the harmonic series. And the reason for that, in case you're curious, is it has to do with music theory, specifically cutting the string in half produces a new sound. Cutting the string into a third creates a new sound, and so on and so forth. That's where it comes from, actually. But the question that we are going to be asking frequently in this class is whether or not something converges. And what mathematicians notice is we learned with improper integration, that the integral from 1 over x from 1 to infinity, that is divergent, right? We learned that during 3.1. Yeah, 3.1. But if you can visualize the harmonic series as this sum of these red, green, and red blocks, you'll notice that it's really just an integration of the function over that interval. Now, I'm cheating a little bit with the fact that this one is actually starting from x equals 0 to infinity, but the idea is still the same. You can either shift it a little bit so that it's underneath, giving us a little bit of an under approximation of the area, or you can shift it to the right a little bit and it becomes an over approximation of the area. But in general, what that led to is a question about whether or not there was some connection between the integration and the series itself. And that gave us a thing called the integral test. Now, probably one of the most technical out of all of them because it has a lot of requirements. Suppose f is a positive, continuous, and decreasing function on the interval capital N to infinity for some n value greater than or equal to 0. You can even bend that a little bit to make it capital N is greater than or equal to like negative numbers, like a fixed negative number, if you want your sequence to start at negative numbers. But as we've seen, we usually like our sequences to start at either n equals 1 or n equals 0. Then the series that starts at k equals n. So I want to kind of highlight this for a second. It starts at n, and that thing is consistent throughout. That capital N has to be consistent throughout. Then the series starting at k equals n, which the sequence is defined by just plugging in all the integers into the function, or the whole numbers into the function. Then the series and the improper integral either both converge or both diverge. That is the rule. And it's a great proof. If you're concerned about it, all three suppositions get used in the theorem. So that's why they're all there. Positive, continuous, and decreasing are all needed. Positive so that you can set up the inequalities properly. Continuity so that you can actually integrate, as we've learned in Math 181. In order to integrate a function, it needs to be continuous or at least a finite number of discontinuities. But more on that in upper division math courses. And then the fact that it is decreasing also plays a role. So the typical usage of the theorem is you'll have a series that you don't know about. You want to figure out more about it. And you look at the improper integral that it corresponds to see if that diverges or converges. And if it does, then yours will result in a converge or diverge. So what I mean by that is if the integral from n to infinity of f of x is divergent, then the sum from k equals n to infinity of a sub k is divergent. And if it's convergent, then it's convergent. Just to save on time, quotation marks meaning the same thing repeated, just changing the words to convergent instead. So what you're trying to do is you're trying to figure out whether or not the improper integral converges or diverges. And if it does, then you know your thing results in it. And so as my notes said, and I already mentioned above, the n needs to be consistent. In order, like this is more of a technicality, but mathematicians are a stickler for technicalities. If it ends up being a situation on an exam, you'll see on the very first example of why this like how we have to skirt around this rule. If this were to show up on an exam and you missed that fact, it would be a situation where you might have seen on my exams where it says correct this and I'll give full credit back, because it is an easy mistake to make, and it's just a silly thing that we have to do in mathematics. Next thing, very, very important. If the improper integral converges to some finite number L, that is not what the series converges to. That is merely an estimation. Usually it's an upper bound. Sometimes the lower bound, depending on the function, but for the most part, it's usually an upper bound, but it's not what it actually converges to. Case in point, Euler figured out it requires a little bit of heavy mathematics, but this actually equals pi squared over 6, which is bonkers if you think about it. That an infinite number of squared fractions adds up to pi, adds up to a multiple of pi. That is really, really cool. But what you originally find out is that if you integrate this from 1 to infinity, I believe you get 2 as your answer. It's been a hot minute. And so you know an upper bound is 2, but you don't know exactly what the actual value is. So the improper integral and the actual series do not have the same convergent value. And then you need all conditions to be met in order to use the theorem. So those are, once again, it needs to be positive, continuous, and decreasing. You need to check all 3. And if one of them fails, you cannot use the test. So it's definitely one of the most technical. So here is the integral test. Let's go ahead and box it in because this is another one of our tests. On our review day on Tuesday of next week, I will be like the thing I'll be sending you guys out, or we'll have it in class that day, the cheat sheet, if you will, of all the tests that will be provided on the exam. So when it comes to finding out how a function is decreasing, there are 2 main ways. There's probably more, but these are the 2 most common ways to do it. So you can either, 1, use the first derivative test from Calc 1, right? Find the derivative, find its critical values, set up a sign chart to figure out where the function is increasing, where it's decreasing. Or you can prove, that a sub k is greater than or equal to a sub k plus 1. So that would let's take a second to write that down and then understand what's going on here. So the first derivative test is always a great option. However, it does take time, right? Finding a derivative can be a little tedious, setting up the sign chart, figuring that out, it can take time. Sometimes it's the only way to do it, but other times it's not. That is one way, or you can look at it systematically. So if a function is decreasing, that means that every subsequent piece is now smaller than the previous one. So a sub k should be larger than the next one in the sequence, and so on and so forth. So if you can prove that, that's excellent. And you'll be better than most Americans. Because remember that whole thing about fractions, right? The 1/3 versus the quarter pounder, the 1/3 pound beef versus the quarter pound of beef. The larger the denominator, the smaller the fraction, right? The larger the denominator, the smaller the fraction. So for example, to show you how to use number 2, so I'm going to draw a little red arrow. This is an example of number 2. If an is equal to 1 over 2n plus 1, I want to look at the next term in the sequence and see if it's smaller. If it is, then it's decreasing. If it's not, then it's not decreasing. So a sub n plus 1, remember, that's not going to be like, it's kind of like function composition. So this is what John Doe student does, and John Doe student's wrong. So don't write this down. They write 1 over 2n plus 1 plus 1. That's not correct. It is 1 over the quantity 2n plus 1 plus 1. Because we are replacing n with n plus 1. We're not just adding 1, we're replacing our n's with n plus 1s. So a sub n plus 1 would be 1 over 2 times n plus 1, which is equal to 1 over 2n plus 3. So is that decreasing? Take a second. Like don't answer out loud, but like convince yourself of whether or not it's decreasing. I'm going to help us work through it in case you're stumped. 2n plus 1 and 2n plus 3 are going to be numbers. 2n plus 3 is larger than 2n plus 1. It's 2 points larger. It's 2 integers larger. So this has a larger denominator, meaning that it's a smaller fraction. So it's a smaller overall number. So a sub n is decreasing. So it's really, really great. Proving it that way is really, really great if you have a fixed number up top. So you only have to compare the fractions. You only have to compare the denominators of the fractions. But as you see in this example here, which, by the way, this is going to equal, we'll wait for a second. Does anybody have any questions on the example that was just presented? So you kind of have to reason your way through it. So you have to show, thus, a sub n is greater than or equal to a sub n plus 1, which implies that a sub n is decreasing. You need to show that. And it's like you should, like, if it's something like this, you can claim it. But if you're trying to show for the next one, that's a bold claim to support without any evidence. So we'll see it in just a moment. The proving a sub k is greater than the a sub k plus 1 is really, really great, as I said, if your numerators are fixed. Because otherwise, they will probably be increasing at the same rate that the denominator is increasing. And so it's hard to tell exactly what's going on. So for example, on this one, ln of 2 over 2 plus ln of 3 over 3 plus ln of 4 over 4. That is equal to the series from k equals 2 to infinity of ln of k over K. We all see that? I mean, you could also write it as the series from K equals 1 to infinity of ln of K plus 1 over K plus 1, or you could start it at 3 or whatever it may be, however you want to write it, but this would probably be the best choice to choose. So here, then, f of x is equal to ln of x over x. Now, as I said, remember, the first test you should always, always, always try. Because if you can prove that the limit does not equal 0, you are done. You can immediately claim that it's divergent and call it good. Remember, that was the divergence test, which says that if the limit of the sequence is not 0, then the series must diverge. If the sequence approaches 0, doesn't approach 0, the whole series diverges. So we look at the limit as n approaches positive infinity of natural log of n over n. But we learned, and you can use the L'Hopital's rule, but remember, natural log grows so much slower than any power of n, so this does equal 0. You can use L'Hopital's rule to verify that too, because you'll get, if you take the derivative of the top, that's 1 over n over 1, and that will approach 0. So the divergence test fails. So inconclusive. Sad days. Right? It didn't work out, so we have to do more work. But it's one of those things, if you can check it and it works out, kind of like with limits. Remember, with a limit, if you wanted to know whether or not it existed, you should always plug it in first to see if you get a finite number. And if you do, you're done. Otherwise, you need to do some work. Same thing's true here. So we should always test the divergence test first. Since that did not work, we'll go on to trying to use the integral test, because that's the only test we've got right now that works with this type of a thing. Any questions on that? Okay, so first thing to check, is it positive? Because remember, natural log can be negative, right? Natural log looks like this. But what's this number right here? You remember? Very close. 1. Natural log of 1 is 0. So after 1, natural log is always positive. And after 0, x is always positive. So for all x greater than or equal to, for all x greater than 1, ln of x over x is positive. So check mark. That has been proven. So if you're on an exam and you need to use the integral test, you need to show this. You need to show that it's positive. Is it continuous? Remember that all of the functions that we learned about, every single one of them, they are continuous on their domains. The domain of this function is all numbers strictly greater than 0. F of x equals ln of x over x is continuous on 0 to positive infinity. So remember that we needed it to be capital N in the integral test. So since it's continuous on 0 to positive infinity, so let's actually add like not a check mark. Thus, continuous on bracket 2 to positive infinity. Because it's continuous from 0 to infinity, it must be continuous from bracket 2 to positive infinity. Any questions so far? Those are the two nicer properties to prove. Now, decreasing. Showing that a sub k is greater than a sub k plus 1 is faster. But if we try and do that here, don't write this down. A sub n is equal to natural log of n over n. And a sub n plus 1 is equal to natural log of n plus 1 over n plus 1. Now, we do know, all of us do know, that natural log grows slower than the linear function n. However, it is a very bold claim to say that this is actually smaller. Yes, it has a larger denominator, which means that you're dividing by a larger number, making it smaller, but its numerator is also larger. So it's very, very unclear whether or not it's actually decreasing, because natural log and n are both increasing as we move on. Does that make sense? So this doesn't work out. And if you were to try and write that on an exam, I'd say that's a bold claim. You need to prove that. And proving it by hand is a little bit of a tedious thing. It's better to use the first derivative test. So in order to do the first derivative test, we need to find a derivative. So f prime of x by the quotient rule is 1 over x times x, f prime g minus g prime f all over g squared. F prime g minus g prime f all over g squared. Okay. And that will equal 1 minus natural log of x divided by x squared. Setting the derivative equal to 0 slash dne, because that's how we find critical values, is just as a reminder. It's been a while since we've had to do this. Since 181, we haven't even needed to do it in any of our other sections. But in order to find critical values, you set the derivative equal to 0 and also find where it doesn't exist. And that would give us 1 minus ln of x over x squared would equal 0. So we get f prime equals 0 if 1 minus ln of x is equal to 0. And how do we solve that? Logarithmic equation. We remember? What do? Someone throw out a crazy idea. It's kind of like a linear equation, isn't it? Like if I were to erase the natural log here, the way we solve it is we either add x to both sides or subtract -1 and then divide by -1 at the same time. Same thing is going to be true here. This means that natural log of x is equal to 1. And then you can either, there are two methodologies on how to solve a logarithmic equation like this. The way I typically teach it is by converting it to exponential form. Natural log, what's the base on natural log? Common log is 10. E is the natural base. So we start at the base, work across the equal sign, and then back over to get that e to the first power is equal to x. The other way to do that, in case you want to see a different way, I'm going to erase this for just a second. I don't recommend this, but you can do this. You can raise both sides, like e to the ln is therefore equal to e to the 1. The e and the ln cancel, leaving us with just an x, and we get the same answer. But this is the more technically correct way, I guess. Is that okay? Any questions on that? We good? And then f prime is dne here. So x squared equals 0, which gives me x equals 0. But that's not in the domain. So nuance is important here, right? Our domain is all numbers strictly greater than 0. So we can't even plug in 0 into our function. We get natural log of 0 over 0. That's like doubly bad. Natural log of 0 doesn't exist, and we're trying to divide by 0 at the same time. It's just a bad time. So our only critical value is E. So we'll make a sign chart, and we'll start it at 0. And here is E. And this is the F prime sign chart. This is the way I set them up. But if you learned a different way in your calculus class, please feel free to do it. As long as you are showing that a first derivative test in some way, shape, or form, I am cool with it. Now, luckily, you guys have a calculator, unlike me in my grads class, where I had to figure out what E squared was without from memory. Does anybody know what E is approximately? 2.71 is exactly right. That's a good approximation, just like 3.14 is a good approximation of pi. So this is approximately 2.71. So if we're going to set up a system, if we're gonna choose some test points, we'll choose x equals 1 and x equals 3. You could choose x equals 2 for the first segment as well. Or I've had plenty of students do this where they go like 0.00001 just to troll me. It's fine if you want to. But either way, natural log of 1 is 0. So we have 1 minus natural log of 1, which is 1. So that's positive. And 1 squared is positive. So it is increasing over here. And then at 3, 1 minus natural log of 3. 3 is a little bit bigger than E, so natural log of 3 will be larger than 1. So it's going to be negative over a positive, which is decreasing. Any questions on that? So here's a pretty interesting nuance. It's decreasing on E to positive infinity. But we start our series at k equals 2, right? Oh man, I am running out of space. I went too crazy with my my spacing. Oh well. We'll be fine. We'll be fine. So decreasing on E to positive infinity, or roughly 2.71 to positive infinity. But that does play a role later on. Okay, so we've checked all 3 conditions, and it's taking a lot of time because we're going through all the motions for this first attempt. And I promise it's usually a little bit faster than this. But because this one has nuance, we got to take time. Since all 3 conditions are satisfied, we can now check the integral, the improper integral, and see if it converges. And if it does, our overall our series will converge, and if it doesn't, our series will diverge. So by int test, the integral from 3 to infinity of ln of x over x dx. I'm doing 3 because I'm not increasing at 2. I'm trying to pick an integer that is inside my interval. 2 is not, so it's not decreasing at 2, so I have to start with 3. So if you remember our methodology of doing improper integrals, we first need to rewrite this in limit notation. The limit as b approaches positive infinity. Integral from 3 to b of natural log of x over x dx. And then what I'm going to do is I'm going to compute this integral off on the side. because I don't want to have to keep rewriting the limit over and over and over and over again. So let's go ahead and do that. Got the integral from 3 to b of ln of x over x dx. And that does not require any integration techniques, at least not yet. Right? It is not a trigonometric integral. It's not a trig sub. It's not an integration by parts. You can actually do this one quite quickly with just a u substitution. If you make u equal to natural log of x, then du will equal 1 over x dx. And notice that that'll allow this over x dx to cancel. So this is equal to the integral from blah to blah of u du. Any questions on that? So, I mean, I guess I technically should write from x equals 3 to x equals b, but dot to dot, I'm changing up my opinion on things. So this is equal to u squared over 2 evaluated from dot to dot, which is ln of x squared over 2 evaluated from 3 to b. Any questions on that? Okay, so I'm going to go back to the limit now because I can find what that difference of two things using the fundamental theorem of calculus is. It's going to be the limit as b approaches positive infinity of ln of b quantity squared over 2 minus ln of 3 quantity squared over 2. And will that blow up to infinity or will that converge? As the limit approaches infinity for b. What do you think? Infinity, yes. Jonathan's absolutely correct. Because as b goes to infinity, natural log of b will go to infinity, albeit very, very slowly. It grows very, very slowly, but eventually it does reach infinity. So this equals infinity, which means that it is divergent. So the series from k equals 3 let's highlight that in red, to infinity of ln of k over k is divergent by the int test. But that's not our series. This is where that technicality comes into play. And yes, it's annoying, I know, but it's required. And that's why this problem was there. I try not to do it on exams, but if I did, remember that it's okay if you make that mistake and claim that the series from k equals 2 to infinity of ln of k is divergent. I'll just mark it wrong and say, correct this. I'll circle, if this was on the exam, I would circle this and cross it out and say, fix this, and you'll get full credit back, because that's a really lame way to lose points for that thing. But the series from k equals 3 to infinity is divergent by the integral test, and thus the series from k equals 2 of ln of k over k, which is equal to ln of 2 over 2 plus the series from k equals 3 to infinity of ln of k over k is divergent as well. Is it technically Is this really one of those things that I'm willing to die on? Yes, because I would get marked down on it. If I'm going to get marked down on it, so are you. Because I love being that guy that makes it actually, actually it's not correct. It's way too fun to do that, to be technically correct. Do we all see the nuance? So you can remember what we learned is that you can take terms out of your sequence to get it to start with a new index. So we know that k equals 3 is divergent, and because the sum from k equals 2 to infinity is just a finite number, ln of 2 over 2 plus our previously divergent series, the whole thing is divergent. Any questions on that? Derek, yes. Yes. So the integral test takes a long time. Now this one, once again, this was very, very long for several reasons. Number one is we had to use the integral, we had to use the first derivative test to prove decreasing. And that took a long time. The other reason this is going to happen regardless, showing the improper integral takes time. It does. And furthermore, the last thing is the fact that this started with a number that was outside of our range. That was extra nuance. Normally, it doesn't take this long. So you'll see that on the next example. Any other questions? So this one, determine if the following series is convergent or divergent. Well, div test. Because remember, that's what we should always try and do first. The limit as k approaches positive infinity of 1 over k squared plus 1. Please, please not equal 0. Damn it. It is inconclusive because the limit does not equal, because the limit equals 0. And the good news about this one, by the way, we're going to learn a test in just a minute that actually proves that this is convergent without having to do integration. But we'll get there. So at this juncture, the only other tests that we know of, the only tests we know of are the geometric sequence test, but this isn't a geometric sequence, or the integral test. And so f of x equals 1 over x squared plus 1, decreasing, positive. Yup. Right? K squared is always positive, or x squared is always positive. Adding 1 to it makes it more positive. Its numerator is positive, so it's always positive. Cool? Continuous. Yup. It's a continuous function everywhere, in fact. Because it has no problems in its domain. All functions that we will encounter in 181 and in this course are continuous on their domains. There's very few functions where that's not true, and those are for math majors to be concerned about. So as long as you find the domain of the function, which in this case, it's everything, because the denominator never equals 0. That's the sum of squares. That's always positive. So it is continuous. Decreasing. Let's look at a sub n, which is 1 over n squared plus 1, versus a sub n plus 1, which is 1 over n plus 1 squared plus 1. Is a sub n plus 1 smaller? Let's reason through it together. Is n plus 1 squared plus 1 larger or smaller than n squared plus 1? It's larger, because we're taking a number that's bigger than n and squaring it, so it should be bigger, right? 2 squared is smaller than 3 squared. So this has a larger denominator, meaning that it is a smaller number. A sub k plus, or a sub n plus 1 has bigger denominator, which implies that a sub n is greater than or equal to a sub n plus 1. Check mark. All three conditions are satisfied. Any questions on that? Then we will look at the integral test. We'll look at the integral from 1 to infinity of 1 over x squared plus 1 dx. Because it is positive, continuous, and decreasing, we can use the integral test, which means that we look at the improper integral starting with our desired number. We started at k equals 1, so we should start at k equals 1 as long as we can. We couldn't do it in the previous example, but we can do it here. So this will equal the limit as b approaches positive infinity of the integral from 1 to b of 1 over x squared plus 1 dx. Now, the good news is this one doesn't require anything to find the antiderivative of. We know what that antiderivative is, right? Tangent inverse. 1 over 1 plus x squared, or 1 over x squared plus 1, however you want to write it. It is tangent inverse is antiderivative. Or derivative. So this is equal to the limit as b approaches infinity of tangent inverse of b minus tangent inverse of 1. Now, here's the question, though. Do you guys know what tangent inverse approaches as b goes to positive infinity? I wouldn't expect you to. What is it? That is correct. Parker is absolutely correct. It's pi over 2. Very, very good. If you look at the graph of tangent inverse, now if this was important, like if this was like I wouldn't expect you to memorize this, but this is the way tangent inverse looks like. Tangent inverse looks like that function where this is pi over 2 and this is negative pi over 2. So it does converge. So this will approach pi over 2. And what will tangent inverse of 1 be equal to? The way you answer that question, the way I've always done it, because I don't have them memorized, I have to ask myself, what value of theta makes tangent of theta equal to 1? Pi over 4. Some small nuance on notation. Please note that I made an arrow here, but I used an equal sign here. This approaches pi over 2. Its limit is pi over 2, but this is a finite fixed number of pi over 4. So this equals pi over 4, which is therefore convergent. So the series from k equals 1 to infinity of 1 over k squared plus 1 is convergent by int test. And sadly, we're not going to get a break today. We got a lot to do, so we're not going to take a break. Maybe we'll take a 3-minute break to kind of get standing up and stretching out a little bit, but we've got some stuff to do. So, any questions on that? If this was on an exam and you didn't know about tangent inverse and I didn't provide it, what I would recommend that you write is, I don't know whether or not this is convergent, but if it is, then this is convergent. If not, it's divergent. And I would give you most of the points. I'd give you probably an 8 or 9 out of 10. Because you know exactly how everything works. You just didn't remember what the graph of tangent inverse looks like, which, unless you're a math person, unless you're a math major, why would you know that? It's not very, very useful information. Something you can look up in a book. So, cool? So cool. All right. The next one I'm going to save for you guys. unless we have time at the end, this one will be convergent. I recommend trying to do that on your own time. You're going to need to use, well, wait a minute. We can prove decreasing. We can prove decreasing without using the first derivative test. When I initially made this in my notes, I had to use the first derivative test. But let's prove decreasing real quick for you. A sub n is equal to e to the 1 over n over n squared versus a sub n plus 1, which is equal to e to the 1 over n plus 1 over n plus 1 squared. It's very, very clear that the denominator gets bigger, correct? Right? N plus 1 squared is bigger than n squared. E to the 1 over n plus 1, that is a smaller number. E to the 1 over n plus 1 is a smaller number than 1 over n and 1 over n, right? So e to the 1 over n squared would be smaller. Note, e to the 1 over n is larger than e to the 1 over n plus 1, and n squared is less than n plus 1 squared. So e to the 1 over n plus 1 over n plus 1 squared is less than e to the 1 over n squared. Let's make sure we understand that one more time. Let's talk through it one more time because it's a lot of mental gymnastics. And that's good for your brain. It's very, very good for it. So it's very, very abundantly clear that the denominators are getting larger, meaning that the overall, if the numerator was fixed, if it was a fixed number, this would definitely be smaller. However, because the exponent on the e is 1 over n, that means that if we go a further one in the sequence, 1 over n plus 1, this is going to be a smaller number because there's a bigger denominator. Meaning that the e value, because e is an increasing function, if I plug in a number smaller, I get a smaller value. So this is smaller, this is bigger, resulting in a double whammy, if you will. Both the numerator is getting smaller and the denominator is getting bigger, so it's getting even more small. Cool? So prove it on the rest is all for you to do. Find the improper integral, show that it's convergent, and therefore the full thing is convergent, okay? Do that a little later today. You'll be happy that you did. All right. The P series test and the n log P series test. So for P strictly greater than 0, the series from n equals 1 to any series from n equals 1, n equals 3 billion, n equals 5, whatever it is, to infinity is called a P series. And if you have 1 over n times log n raised to the p, it's not n to the p, it's n times log n to the p, is called an n log p series. And so we have the P series tests. So please notice that I made it tests. That's the big S. Yes, to exaggerate the fact that this is both for the P series and the n log P series. Both of these series will be convergent if P is strictly greater than 1, and they will be divergent if P is less than or equal to 1. Textbooks will say, most textbooks will say if P is between 0 and 1, but you don't need to. And if P is negative, then that just flips it up top. And then you're dealing with a thing that doesn't converge at all. So you can actually make it more generalized and say convergent if P is strictly greater than 1, divergent if P is less than or equal to 1. So the shorthand is that the series from n equals blah to infinity of 1 over n to the p and 1 over n log n times log of n to the p are convergent if p is greater than 1, and they are divergent if p is less than or equal to 1. That's the shorthand version. That is the next series. How do you think you prove that? The integral test. Because both of those functions are continuous for all numbers greater than or equal to 0. They are both decreasing. They are all positive after n equals 1. So the n log p series has to start at n equals 2, because otherwise you got natural log. Not log. ln. Sorry. I'm used to seeing it like I have nightmares about the way I saw it in my old textbooks. Back in the day, back in my day, right? When dinosaurs ruled the earth, all the textbooks, they used to write it as log. So common log only recently became log base 10. A lot of old textbooks, when they wrote log, they meant natural log. So the way it was written in my textbook growing up, back when TV was still in black and white, it said log. So I'm just having a moment. So anyways, convergent if p is greater than 1, divergent if p is less than or equal to 1. So first one, you can try the divergence test, and we should. Natural log, or sorry, not limit. Limit as n or let's use k. K approaches positive infinity of 1 over k to the 5/7 will equal 0. So it's inconclusive. Sad day. Now, do I need to do that? Just like with limits, right? Remember when we started doing limits, we would kind of just check it in our calculator or check it in our head whether or not it actually existed. And if it did, cool, then we'd actually go through the work. Otherwise, we just move on, right? You remember that? Same thing here. I'm writing it, but you can do it in your head to see it first. And if it does equal 0 in your head, don't even bother writing it down. That'd be additionally, as soon as I saw 1 over variable raised to a p-value to a number, I thought the p-test. That is definitely the correct choice. Now, p is equal to 5/7, and that is less than or equal to 1. So it is divergent by p-test. That is going to be something that you're going to start seeing, and it's expected of you in this course, is you need to explain which test you use. Because remember my rule about how much work you need to show. Do you guys remember what it was? It should be enough work so that your colleagues know what you meant. And if you don't write what test you're using, they'll be like, okay, it's divergent, but what did you do? What do you mean by P? What is going on here? Derek. Great question. I have no clue. I think whichever mathematician thought of it, they decided to use P as an exponent. Maybe it was some dude named Paul, and they just wanted to put their name into things. They just wanted to troll everybody, so they did it. Just like the person who made the Optimus function for derivatives. Hence, you get Optimus prime. I'm kidding. There's no such thing as the Optimus function. I wish there was. That'd be hilarious. Also, if you plan on taking Calc 283, you'll talk about curl functions, and that uses a del symbol, which is an upside down delta. And I wanted to make the del taco function. I thought it'd be hilarious, but I couldn't think of a cool function to deal with, so I didn't do it. Okay, so I don't know why it's called the p-test, sadly. I think the best choice is just they chose p. If they had made it 1 over n to the k, they would have used the k-test. All right, the next one. 1 over 1 plus 1 over 4 times the cube root of 2 plus 1 over 9 times the cube root of 3 plus blah, 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 blah. Well, notice that that's 2 squared. That's 3 squared. And that's 4 squared. So this is actually equal to the series from n equals 1 to infinity of 1 over n squared times the third root of n. Now that's a p series, but it doesn't look like it at first. But remember, the third root of n, that's equal to n to the 1/3 power. So this is actually equal to the series from n equals 1 to infinity of 1 over n to the 7/3. Right? Because n squared is 6/3. So n to the 6/3 times n to the 1/3, you add the exponents, you get 7/3. So convergent or divergent? P-value is 7/3, which is larger than 1, strictly. So convergent. P is equal to 7/3, which is strictly greater than 1. So convergent by p-test. Last one. Convergent or divergent? Conversion. Your p-value is equal to p is equal to 1.00001, which is strictly greater than 1. So convergent by n log p-test. And I am a generous teacher. If you write conversion by the p-test, I will accept that too. It is basically, it's another type of p-test. So if you say conversion by the p-test, I know what you mean, and your colleague would know what you mean. You don't need to specify n log p-test, but I will write, I like, if you write p-test, I will, like, if you don't write this, I will go like this on your exam, but I won't mark you down because I'm a Starbucks barista at heart, and I have to correct you when you don't say caramel macchiato. You say caramel macchiato, I gotta correct you. They hammer it into you until you have no individuality left at Starbucks. It's true. Cool. So p-test, very, very good. Very, very, very useful. It's probably one that, like, besides the divergence test, it's probably the most commonly used test, though you wouldn't think about it until you see the next tests. All right. Next one, the comparison tests. We have 2 different types. There is the harder one to use, the direct comparison test, and then the one that everyone loves, which is the limit comparison test, which we'll get to. So suppose that A sub n and B sub n are sequences such that A sub n is smaller than B sub n for all n. Theorems, so in case there's any sleeper agents out there who are secret mathematicians who are trying to catch me off my guard, technically I should say, don't write this down, for n greater than or equal to n sub 0 for some n sub 0 greater than or equal to 0. I technically should say that. So because mathematicians like to make these things as generalizable as possible, the theorem is still true just so long that after a certain point, B sub n becomes larger. It doesn't always have to be larger. It's just after a certain point, B sub n becomes larger. It's a silly thing, but mathematicians are silly. So back to the point, A sub n is always less than B sub n, less than or equal to. If A sub n is divergent, then B sub n's series is also divergent. And if B sub n is convergent, then A sub n is also convergent. This is one of those tests that doesn't really require much memorization. It makes sense, right? Imagine this fact right here. I'll put a little asterisk here. This means that 0 is greater than or equal to, less than or equal to the series of A sub n is less than or equal to the series of B sub n. Right? So if A sub n is divergent, that means it blows up to infinity or something. So B sub n is larger than infinity, meaning it also has to blow up. If B sub n is convergent, it's finite, which means that an is the series of A sub n is also finite. It has to be because it's sandwiched between 0 and B sub n. So this is one of those ones, it kind of makes sense, immediate. It's great. So determine if the following series are convergent or divergent. We have the series from n equals 1 to infinity of 1 over 3n squared plus 2. Now, looking at that, that's very, very similar to just 1 over n squared. Key trick. I need to add this to it. Main way to use. Take a known series for your comparison. Maybe that's inherently clear to you. If it is, kudos to you. But what do I mean by this? Now that we have the n log p test and the p test, we now know a very, very large group of series that are convergent and divergent. We know that 1 over n is divergent. 1 over n to the 1.01 is convergent. 1 over n squared is convergent. 1 over n to the 15th is convergent. 1 over n to the 0.2 is divergent. We now have a huge list of things that we can compare to this. And in addition, any test that you find out earlier on, so 1 over k squared plus 1, we just learned that that was convergent with the integral test. So we could utilize that series to our advantage. We know that 1 over natural log of n over n, as n goes to infinity for values larger than 2, we know that one is convergent or is divergent. So if we can sandwich it in a certain way, we can prove things. So looking at this one, note 1 over n squared and then 1 over 3n squared plus 2. Which one's larger? Take a second, don't answer out loud. Should I write a greater than or equal to or a less than or equal to? Take a second. Deduce it in your mind. Maybe you're better than me, but it always took me a bunch of deductions in my head to figure it out. But it's good. It's like doing a little bit of weights for your brain. Should it be a greater than or should it be a less than? So red or green? Savannah says red. We all agree? If you don't agree, let's work through it. 3n squared plus 2 is a larger number than n squared. It just has to be. So that's a larger denominator, which means an overall smaller number. So it's the red. Note, that's true. And we can write larger denominator. Smaller overall. The thing I'm writing in purple is something that you don't have to write down on an exam. You can just claim it because that is apparent enough. Now that we've been doing it enough, that is something you can say. This means that the sum from n equals 1 to infinity of 1 over 3n squared plus 2 is less than or equal to the series from n equals 1 to infinity of 1 over n squared. As the series from n equals 1 to infinity of 1 over n squared is convergent by p-test, you don't need to write the by p-test. That is a known fact while we're proving this problem, but it doesn't hurt to write. This is finite. And because this is finite, this has to be. There's no other way. It converges to a smaller number. What number it is, we have no clue. But we do know that it exists. So our series is convergent by direct comparison. So that is our answer. This was our work. This is our answer that we box in. Any questions on that? How are we all feeling? Because I'm having a hard time reading the faces right now. Derek, you have a question? Yes. As long as you can find a series that you can relate to your desired series, you can use it.
What's the conditions for it being related?
You just need to find a way to show that the known series is either larger or smaller. That's it. And then you have to know where to sandwich it. So great point. Let me bring this up. So this is a situation where it doesn't help. So this one thing you could argue is you could say, well, I know that 1 over 3n squared plus 2 is less than 1 over n, right? That's true, because n squared is just going to be even larger than n, so this is true. This is divergent, but that has no bearing on this, because that's just an upper bound. All that's saying is that it is less than infinity. That's not enough. Whereas if we know, like when we have this we can use because we know that this blows up to infinity. So our series is going to have to blow up to infinity as well. But right now, this doesn't tell us anything. So that's kind of a shortcoming of it. And that's a mistake that some students make. Does anybody need me to explain that in a different way? Yeah. Okay. So this is divergent. We've proved that with the n log p with the p-test. But just because this is divergent, that just means that this thing is less than infinity, like it less than or equal to infinity. It has no idea whether or not this is finite. So it doesn't do what we need it to do. If I were able to flip this around and know that this was infinite, then this also has to be infinite. But that's not the case. So this current format doesn't do anything for me. It's why I had to choose n squared instead. But as long as you can find a series that you can relate to it and properly sandwich it the right way, you can use the direct comparison. This next one, series from k equals 2 to infinity of 1 over ln of k. What is a thing that we know that grows faster than natural log? K. Yeah. As k is greater than natural log of k, 1 over k is less than or equal to 1 over natural log of k. That's true, right? K will have a 1 over K will have a larger denominator, meaning that it'll be an overall smaller fraction. So that means that the series from K equals 2 to infinity of 1 over K is less than or equal to the series from K equals 2 to infinity of 1 over natural log of K. And this, well, as the series from K equals 2 to infinity of 1 over K is divergent by Peace test, our series is divergent by direct comparison. As a small aside, just in case, if you like this, try and take more upper division mathematics. This is the start of a thing called real analysis, which is a 400 level math class. A lot of universities will have an introduction to real analysis, which is usually a 300 level math class. So if you like this concept, if you like proving these things, you're in good company with me. So I'm a math major. I loved doing this when I was a student. From my experience, most students do not like this. So I'm hoping to change that. It's fun. It's fun messing around with these theorems and trying to prove things. It's a deduction process. It's great. This next one, e to the m over m plus 1. Ooh. What should I use to compare that? What should I do? Say what?
E to the M over M.
E to the m over m? That's good too. That'll but then the question is, what is e to the m over m? Is that convergent or divergent? Yes, you could. Yes. With integration by parts, and it would work. It would take a while, but there's a much simpler option. What's the test you should always do first? The divergence test. Remember, E grows a lot faster than M. E grows a lot faster. So note the limit as m approaches positive infinity of e to the m over m plus 1 equals positive infinity. So divergent by the div test, by the divergence test. Yay. Gotta love a good divergence test problem. This was to remind us that you should always, always, always try the divergence test first. I didn't do in the previous examples, and I did that on purpose because I want you to know that it's very common. I don't have my notes for this section because it's a very common thing that even I do, where I get so bogged down with trying to look at different tests that prove convergence that I don't even bother to look and see whether or not it was divergent in the first place. Don't be me. Be better. Always test with the divergence test first. If you do that on every problem, it's worth 1 or 2 points, right? That's some work trying to figure out divergence. It's kind of like in Calc 1, right? It was always a good bet to take the derivative. Even if you don't know what to do with it, take a derivative, you'll probably get 1 or 2 points. Same thing's true here. Try the divergence test. If it works, it works. If it doesn't, keep working. All right. Any questions? All right. Now, this is the one that a lot of students love far more, and it's very, very clear why it's far better. Because you don't have to sit there and try and think about which one's larger and which one's smaller. The direct, oh, that's supposed to say limit comparison. That's supposed to say limit comparison. Apologies. I'm going to make a note real quick to myself. Unit 3.6. Correct last theorem to limit comp test. Just so that I make these edits as we go along. Thank you for your patience. So the limit comparison test. Suppose that AN and BN are two sequences such that both of them are positive. That is kind of needed. You can also, once again, you can bend the truth a little bit and say, suppose that they are positive for all ones after a certain point. If the limit as n approaches infinity of a sub n over b sub n equals a finite number that is non-zero, then either both series converge or both series diverge. Note, if the limit as n approaches positive infinity of a sub n over b sub n equals 0 or dne, test is inconclusive. Did I box the other one? I don't think I did. Nope. Just so that the reason why I'm boxing them in is so that when you're looking back through your notes, if you're trying to like do practice problems, you can find them all very easily by the fact that they're all boxed in. Look through all your tests, figure out which one. So if the limit of that ratio does equals 0 or infinity, there's no information. You need to try it again with a different sequence or try a different test. That's kind of like the divergence test. So part A. So the way we typically use it is, I would say 2k squared minus 1 over 3k to the fifth plus 2k plus 1 is similar to 2k squared over 3k to the fifth. Use 1 over n cubed. So we should always try in the back of our head to try and use the divergence test. But if you do that, because the denominator has a larger degree, it'll go to infinity faster, meaning that this limit will go to 0. So the divergence test doesn't work for us. So we have to move on to different ones. Looking at this one, I'm seeing the ratio between the numerator and the denominator. The numerator is dominated by that k squared term, and the denominator is dominated by that k to the fifth term. So at the end of the day, once we're going into very, 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 very big powers of k, all the other small stuff doesn't matter. So just looking at 2k squared over 3k to the fifth. Now, you could try and use, we could do 2/3, 1 over n cubed, but it doesn't really matter. As long as we find a finite number, we're good. And so 1 over n cubed should suffice, because that's or use k cubed, not 1 over n cubed. Apologies. So at infinity, they kind of look like 1 over k cubed. You guys all see that? Is that okay? We all on the same page with that one? It's okay if we're not. So we'll do the limit as k approaches positive infinity of, and the great thing about this is it doesn't matter which one you put where. You're just comparing two different series. So if you put your original series and your proposed series on the top and bottom respectively, it's the same thing as if you flipped it. So I'm going to put it up here, 2k squared minus 1 over 3k to the fifth plus 2k plus 1 all over 1 over k cubed. but you can do the same thing if you flip it. You will get the reversed fraction, you'll get the reciprocal of what I get, but it will still end up being a finite non-zero number. And that's all you need to do. You need to show that it equals a finite non-zero number. If that's cool, we're good. So this equals the limit as k approaches positive infinity of 2k to the fifth minus k cubed divided by 3k to the fifth plus 2k plus 1, which equals 2/3, which is strictly greater than 0. Let's actually write that in a different color. It's finite. So if you did it in the reverse fashion, you would get a limit of 3/2, but that is still a finite positive number. So either both of them converge or both of them diverge. But we know by the p-series test that 1 over k cubed converges. Since the series from k equals 1 to infinity of 1 over k cubed is convergent by p-test, our series is convergent by limit comparison. This is the start, by the way, of proof writing. This is how, this is a very bastardized version of it. There needs to be more formal language and writing in an essay format in order to prove what mathematicians like you to prove. But this is the start of it. This is a very, very rudimentary form of proofs that we do in mathematics. So once again, if you like this, please come talk to me, and I will talk your ear off about math, being a math major, and advise you to stay against it. It's not a good idea. Okay. And how many more? We got those ones. Okay. So we got a few more to deal with. I think we're going to get through this one and maybe a few on the next page, but otherwise I'd like us to prove them to ourselves on our own time. And then maybe on Thursday of next week, this coming Thursday. Today's Tuesday, right? Yeah. Been a crazy day. I'll have the answers later. Okay. So this one, tangent of 1 over n. Well, it's in the limit comparison section. So what limit do you think we should compare it with? When using limit comparison test and direct comparison test, your bread and butter are the p-series and the n log p-series. So which one do you want to use? What do you think? Throw out a crazy one. Sine over cosine of 1 over n, but then that would be the same thing, right? Good idea. And that actually is going to be what we need to use. So think about sine of 1 over n. Do you remember any special limit with sine? Remember sine of theta over theta? Do you remember that limit? So let's use b is equal to 1 over n. The reason I'm choosing that is because I know what 1 over n converges to, whether or not it's convergent or divergent. It is divergent because the p-value is 1. So let's do the limit as n approaches positive infinity. And it doesn't matter which one you put on top, though I'm going to put tangent of 1 over n up top over 1 over n. Now, this limit can be found in 2 different ways. You can either, as Parker suggested, you can look at this as sine of 1 over n over cosine of 1 over n. And then you have sine of 1 over n. Let me write this down so you can see it. He'll have sine of 1 over n over 1 over n times 1 over cosine of 1 over n. Do we all see how that can happen? It's okay if you don't. Remember that like you're dividing by 1 over n. And this sine of 1 over n, as n approaches infinity, 1 over n approaches 0, so this approaches 1 by that special limit, and cosine of 1 over n approaches cosine of 0, which is 1. So you can do that, or you can lose L'Hopital's rule, right? Because L'Hopital's rule should... Oh, I'm not charging either of these things. Jesus. I mean, we got time. We got time. We've got 5 minutes left. So you could also use L'Hopital's rule. Let's go ahead and practice L'Hopital's rule because I haven't really tested it out in this one. So, wait a minute. That'll just make it worse, won't it? Maybe. No. Wait. Maybe. What happens? Let's just test it out. L'Hopital's rule. We get the limit as n approaches positive infinity of secant squared of 1 over n. Then by the chain rule, because remember, this is tangent of 1 over n, so we need to take the derivative of 1 over n, which is negative 1 over n squared, divided by the derivative of 1 over n, which is negative 1 over n squared. These cancel. So this equals the limit as n approaches positive infinity of secant squared of 1 over n, which will equal secant squared of 0, which is equal to 1, which is finite. And because it is finite, that means that our given series and our proposed series to compare it to either both converge or both diverge. But we know that the series 1 over n diverges, so tangent of 1 over n also diverges. Since the series from n equals 1 to infinity of 1 over n is divergent by p-test, the series from n equals 1 to infinity of tangent of 1 over n is divergent by limit comparison. Any questions on that? So you can prove the limit in many different ways. So that's the key difference between direct comparison and limit comparison. Limit comparison, either both, as long as you get a finite number, either both converge or both diverge. Whereas with direct comparison, you need to find out a way to sandwich it properly. All right, people still writing? Is it okay to move or no, people are still writing, people still writing. I love these tests. These are fun. I hope you guys are also feeling excited. Yes, John.
The 0 is inconclusive.
Yes.
So because it equals 0, you use the original one to see that it diverged.
So the fact of the matter is, as long as when you finally get your limit, you get 1 or some finite number, you know that either both converge or both diverge. If I had compared this with 1 over n squared, I would get an answer of either 0 or infinity, which is a situation where it's 0 or does not exist. So that test would become inconclusive. I would either need to try a different test, or I would need to use the same test with a different sequence. Does that make sense? Great question. So just because you get 0 or does not exist, that doesn't mean you should give up on that test. It just means you didn't choose the right series. Maybe try a different one, and if it works, it works. Otherwise, I would give like 2 attempts and then try something different. If 2 attempts don't work, it's probably a case where you need to use a different test. Okay? Looking at the next ones. So we don't have enough time to prove them. This one is convergent. And you'll need to prove that. And I'm worried about giving away the test that you need to use. I'm not going to tell you the test, but all these ones are all based on limit comparison or like they're all using the tests that we learned now, but you might also need to pull in some old stuff. Specifically with this one. Think about that one. This one is divergent. This one is convergent. And this one is convergent. And there's two different ways you can do D. There's two different ways. There's a long way and there's a quick way. So anyways, feel free to do those ones. I'll have them worked out for us in class on Thursday to look over. Otherwise, you guys have a great rest of your day. I'll see you guys on Thursday. Sorry for no break today, no work on the crossword. Just today's weird day.